Testing, testing, one, two, three. Are we live? Can you hear me? I wasn't going to test this because I noticed I breathe, and then it's very annoying for everyone. So, see how that sounded. I wasn't going to test this because I noticed I breathe, and then it's very annoying for everyone. So, okay, that's not so annoying. Great. I don't know why sometimes it comes through as some weird kind of. Anyway, I can't change it because this is all I got. Okay, cool. Carrying on then. Is there any interesting things to say for the record? I don't think so. Although I watched a video by Sean Carroll um, going through the kind of history of the special general special relativity special special relativity, yeah, from Einstein, and that was fascinating to watch the progression from, and I might get this wrong, but um, Isaac Newton, who came up with F equals ma, and then you had Isaac Newton, who came up with um, g m g multiplied by m small m divided by r squared. I think it's got the e at the end as well, multiplied by e. And then Albert Einstein replacing that with, or discovering E equals mc squared. And then he used things from two other people, I can't remember, and maybe any more, maybe many more. Essentially, Riemann, tensor, all these kinds of things. Basically, lots of different objects that represent the bending of geometry, and it was just fascinating to watch because then it ends up being Einstein's famous equation, well, or not so famous equation, about the bending of space-time. I thought that was wonderful. So that's that. And what I noticed was there was a comment in it which seemed quite relevant to what I'm doing here, which was that um, one of the things you just have to come to grips with is this um, non-symmet non-symmetry or asymmetry with the vectors. And I think it plays a little bit. It reminded me of the fact that actually there was asymmetry in the axiom denoted in this book. So um, maybe I'm on the right track, right? I just realized I've got it. Oh, this one's so salacious. Latex assistance requested. But obviously it's about the latex mathematics. Okay, cool. Let's do this. So, dual spaces and the... Oh, can you actually see everything? Let me just double check. Yes, you can. Not so well, but once again, I can't zoom this in because it's such a shame, actually. It would be so lovely to... Can I just do that? No, and yeah, it just kind of resizes again. Actually, no. In fact, when... Okay, so let me just refresh this page because I think that's gone a bit wonky there. Right. Yeah, shame I can't zoom in. It's even hard for me to read, so yeah, sorry about that. Yeah, okay. Dual spaces and the Dirac notation. So there is a technical point here. The inner product is a number we are trying to generate from two kets, v and w, which are both represented by column vectors in some basis, where basis is a technical term. Now, what does basis mean again? It's it's something where it's uh, I can't remember the terms actually. Let me just remind myself of the terms just quickly. Independent, um, and let me just basis is a set of vectors that through linear combination. So when you add them together, um, can represent every possible vector in the space. So they are, yeah, linearly dependent. Um, is a basis linearly dependent? I could have probably just thought about that myself, but oh well. Independent, okay. The vectors in a basis were linearly dependent, then one or more of them could be expressed as a linear combination. And this is saying uh, basis is basis is a set of vectors through linear combination can represent every possible vector in the space. If some of the vectors were linearly dependent, they wouldn't add any new directions, so they would be redundant in the basis. Therefore, identifying whether a set of vectors is linearly independent is a critical step in. Okay, so the inner product is a number we are trying to generate from two kets, which are both represented by column vectors in some basis. Now, there is no way to make a number out of two columns by direct matrix multiplication, but there is a way to make a number by matrix multiplication of a row times a column. So we're talking about if we had a vector, if you had a vector, I had a vector, everybody has a vector. Um, like this. Um, no, multiplication. So it would be, let's say, oh, I'm a bit close. Maybe I'm a bit close this time. Let me just zoom out my camera here so you don't just see the top of my head all the time, right? Let's try that. Yeah, maybe do a bit more. Sure, why not? That'll do. Yeah, okay, so, um, it says there's no way to, of a row times a column. So a row times a column. So if you've got V1, V2, and you multiply that by W1, W2. I think that's what that's saying, right? Our trick for reducing a number out of two columns has been to associate a unique row vector with one column. A row vector with one column. Its transpose conjugate and form its matrix product with the column representing the other. This has the feature that the answer depends on which of the two vectors we are going to convert to the row. The two choices, VW and WV, leading to answers related by complex conjugation as per axiom 1H. Okay. I don't fully understand what's just been said, but I get it enough. To move on and see where it's going. But one can also take the following alternate view. Column vectors are concrete manifestations of an abstract vector. Concrete manifestations of an abstract vector, or ket in a basis. We can also work backward and go from the column vectors to the abstract kets. We can go from a column vector to the abstract kets. Um, but then it is similarly possible to work backward and associate with each row vector an abstract object W called bra W. Now we can name the bras as we want, but let us do the following. Associated with every ket is a column vector. Let us take its adjoint or transpose conjugate and form a row vector. So let's scribble this out. That's fine. So it says, let us take its adjoint as we want, but let us do the following. Associated with every ket V is a column vector. So every ket V is associated to a column vector. Let us take its adjoint or transpose conjugate and form a row vector. I think essentially because, well, we would imagine that V1 um, might equal um, that's not the term, but might equal uh, 1 plus 2i, right? So I guess when we do that, we do the conjugate, whoops, 1 minus 2i. Let's just read on though. It might tell us actually what it's trying to say. The abstract bra associated with this will bear the same label, i.e. it'll be called that. So it's saying, I think, that this, well, this is equal to this. Thus, there are two vector spaces, the space of kets and a dual space of bras, with a ket for every bra and vice versa, the components being related by the adjoint operation. Related, not equal to. Okay. Inner products are really defined only between bras and kets, and hence from elements of two distinct but related vector spaces. Let me read that again. Inner products are really defined only between bras and kets, and hence from elements of two distinct but related vector spaces. There is a basis of vectors I for expanding kets, and a similar basis I, bra I and ket I, for expanding bras. The basis ket I is represented in the basis we are using by a column vector with all zeros except for a 1 in the ith row, while the basis bra I is a row vector with all zeros except for a 1 in the ith column. Oh, did I do something there? Okay, cool. Uh, okay, great. No, actually, we got it right. So I forgot to put these there, but that's wonderful. Yes, yes, I understood it. Okay, I feel excited. Um, all this may be summarized as follows. Cool. Hey, that's not bad, huh? Where this back and forth arrow means within a basis. Ah, okay. So maybe not quite right because I'm missing this other symbol here. Um, and it means within a basis. So it's saying that this is within a basis of this. what does that even mean? Ket V is in a basis of V because okay. Let me just understand this. So when the book says where means within a basis, is it stating that V oh, how am I going to write this? uh, column vector. I don't know how to write this. Is it that? V1, V1. I guess I don't know if it even understands this sort of thing. V2. I guess if people wrote it like this, that it should understand. But it's awfully down to the spacing, and so I don't know if it's going to understand that. Let's see. Um, is saying is stating that when the book says where means a basis, is it stating that the above um, V can be broken down into its ith into its elements. Um, the elements are linearly independent because it's a basis, and so can form the vector itself. And then we move on to the next part. I'll add the next bit of the equation. I'll show the next bit. This V1 star, V sub 1 star, V sub 2 star, and actually I think I will put the n here because that may have something about it in there as well. I feel like I'm speaking to myself at the moment. I'm so sorry. Dot 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 v n conjugate. So let's take this and just update this one. Well, okay, just need to do that. And then we move on to the next part. It's saying that the column vector can become the book says where means within a basis. Is it stating that the above can be broken down into its elements? The elements are linearly independent because it's a basis, and so we can form the V itself again. Similarly, when the book says it's stating that the column vector can become a row vector because the inner basis. You know what? Can you just help me understand what is meant by it? Yeah, I'm just typing and it's just complete nonsense, isn't it? So let's just see. Sure, let's break down what's happening here. When the book uses the notation and says within a basis, it's describing a series of transformations or representations of the vector v within a specific basis. Um, yeah. Oh, it's lovely that it's done that, by the way. Here, V is being represented as a column vector with respect to a chosen basis. The entries v1, v2 are the components of V in that basis. Since the basis is linearly independent, you can uniquely represent any vector in the space, including using these components. Now the column vector is being transformed into a row vector. The conjugate transpose of a column vector is a row vector, and taking the conjugate transpose involves both transposing the vector, turning rows into columns or vice versa, and taking the complex conjugate of each entry. This second transformation changes the representation from a column vector to a row vector, and the entries are now the complex conjugates of the original components. These transformations are illustrating how you can express the vector v in different ways within the given basis. It highlights how. Yeah, okay. So the wording got me there, but of course, it's very simple. It's just simply meaning that um, all of these elements. Don't want to use my hands. All of these elements are within this basis. Got it. Okay, cool. There is, however, I'm going to go back to the book. There is, however, nothing wrong with the first viewpoint of associating a scalar product with a pair of columns or kets, making no reference to another dual space. What's a dual space? What's a dual space? Concept of linear algebra associated with a given vector space. Given a vector space V over a field F, such as the real or complex numbers, the dual space, denoted as V star, consists of all linear functionals on V. A linear functional is a linear map from V to the field F. Yeah, so the word map, it's quite programmery, I guess, is that you have to transform that vector somehow, and that transformation is a function. That function is called a map because it transforms from one to the other, it maps from one to the other. Imagine if you have a class and properties and you want A to go to B and B to go to A, that becomes a mapping function. Here's a bit more detail. Vector space. A vector space V consists of vectors, and you can add vectors together or multiply them by scalars from a field F. Linear functional. A linear functional is a function f that takes v to f that satisfies two properties. The function um, alpha v plus beta v w is equal to alpha times the function v plus beta times the function w. Um, yes, okay, that makes sense. Yeah, let me just write that. Because I like to write it in my head a bit. So I'm sorry I keep yawning as well. It's whenever I speak on this streaming it gets me going. Let me just put a little wiggly here. We're going to go, it says function, let's do that thing, alpha, because we're talking about space, I guess. So for v plus beta w, and it says it's equal to, and let's do it ourselves. So if you're going to do it, it would be a um, times the function of v plus beta times the function, whoops, times the function w. Now let's do this with some simple things. If you go a equals 2, b equals 3, and v equals 4 and w equals 5, two times 4, well, let's do this. A v equals 2 times 4, beta w is equal to, why have I done that? Should just do beta, make my life easier. Beta is 3, W is 5. Okay, so if we do that, 8 plus like that. Now let's do it the other way. So that's this way. Now I want to do this way. So it's going to be 2 times 4 plus 3 times 5. But, this is a function. So it's actually, it's a times the function of v is equal to 2 times the function of 4. And beta times the function of w is equal to 3, yeah, 3 times the function, ooh, also don't need that, the function of 5. So now we need to define the function. So let's say it's plus 1, or let's say it's times 2, right? So the function is equal to x, 2x. Right so far? Okay. And then so now we're going to do the function. Yeah, okay. Like this, I guess. This leads to 2 times 23, which is equal to 46, right? Where 2 is the function of f of x. And this is x. Okay, let's do this one. So this is going to be 2 times 8, which equals 16, and 3 times 10. And therefore it equals 46. Wonderful. So we just proved that. Okay, cool. That's good. So this really does makes it. I mean, that's obvious in a way if you know the patterns, but it's nice to just show it and remind myself that you can do this sort of thing. Okay, cool. So let's go back to this. A linear functional is a function f that leads from v to f that satisfies. What is this? How should I say? For example, f v f maps to, goes to. Okay, maps to. Good. Okay. So sorry, I've got it. So it says a linear function is a function f that that where V leads to F, maps to F, that satisfies two properties. So it must do that for all vectors V, W as an element of V. For all vectors V, where W is an element of V, and all scalars, alpha, beta, is element of F. F, V plus W equals, yeah, got you, okay. So dual space, the set of all linear functionals on V forms a vector space itself, called the dual space V star. You can add linear functionals together and multiply them by scalars, and they still satisfy the properties of a vector space. We got it. In finite dimensional spaces, there's a natural way to associate each vector V in V with a corresponding linear functional in the dual space. If you have a basis for V, you can define the action of the linear functional on the basis vectors, and this extends uniquely to a linear functional on the whole space. The concept of dual spaces plays a crucial role in various areas of mathematics and physics, particularly in the study of functionals, the formulation of variational problems, and in quantum mechanics, where bracket notation involves dual spaces. There is, however, so I'm going to go back to it. There is, however, nothing wrong with the first viewpoint of associating the scalar product with a pair of columns or kets, making no reference to another dual space. So have I learnt this? This is making no reference to another dual space. A dual space is where the vectors are functions? Functionals on B forms. A linear function is where you can add a function and then add the vectors together. Okay. Wow, this is super abstract, abstract and very explicit. If you found the above discussion heavy going, you can temporarily ignore it. The only thing you must remember is that in the case of a general non-narrow vector space, vectors can still be assigned components in some orthonormal basis, just as with arrows. But these may be complex. The inner product of any two vectors is given in terms of these components by equation 125. This product obeys all the axioms. Expansion of vectors in an orthonormal basis. So let's move this along. I'll draw my little dots again. There and there. And I'll move this one along for us there as well. Okay. Expansion of vectors in an orthonormal basis. Suppose we wish to expand a vector v in an orthonormal basis. To find the components that go into the expansion, we proceed as follows. We take the dot product of both sides of the assumed expansion with ket j colon or bra j if you are a purist. We take the dot product of both sides of the assumed expansion Suppose you wish to expand a vector v in an orthonormal basis. To find the components that go into the what's the orthonormal again? Orthonormal. In orthonormal basis, ij is typically 1 if I equals j and 0 if I... Okay, this effectively means you're summing over all products of corresponding components. Yeah, here we go. What does orthonormal mean? Orthonormality is a concept in linear algebra related to the nature of a set of vectors. A set of vectors is considered orthonormal if all vectors in the set are orthogonal to each other. Their inner product is 0. And each vector has a norm or length of 1. Suppose we wish to expand a vector v in an orthonormal basis. Okay, so an orthonormal basis is equal to a vector whereby a vector whereby v1 equals a null vector and v1 equals 1, v2, etc. Set of vectors set are orthogonal to each other. Their inner product is 0. So actually it's rather that v1 equals 0 or equals 0. That's fine because it returns a single number. And each vector has a norm or length of 1. Yep. And so this one's fine as well. Let's do that's right. We take the dot product of both sides of the assumed expansion with bra j, no, with ket j or bra j if you are a purist. So saying ket v is equal to the sum of vi multiplied by, yeah, let's just write it out because it's just too small, isn't it? So we got v is equal to the sum of vi multiplied by I, and then it says the inner product of j v, let's make that little one, is equal to the sum of, let's see this. Where's the j come from? Aha, I see. Okay. J I, is it? Oh, it's the whole thing. Oh wow, okay. Right, yeah. Where this is the something, someone's name. I can't remember the name now. Let's go back a bit. Kronecker delta is the Kronecker delta. Okay. Equals to Bj. I.e., so yeah, what is it saying? Before I read that, it's saying that the vector is equal to the sum of all the vector's components multiplied by it's the sum of all the components of the vector multiplied by the iterator as a vector. And this is saying the inner product of J and V is equal to the sum of all the components of V multiplied by the inner product of the J vector and the set, the iterator, where this is the Kronecker delta, and it's saying that that is all equal to Vj. I.e., to find the jth component of a vector, we take the dot product with the jth unit vector. We take the dot product with the jth unit vector, exactly as with arrows. Using this result, we may write vector equals ket v equals the sum of ket I multiplied by the inner product of I bra I ket, no, the inner product of I and V. Okay, fine. Let us make sure the basis vectors look as they should. If we set ket v to equal to ket j in equation 135, we find the correct answer. So it says, let me just move this up a bit. Make it a bit smaller. In fact, I'll probably put it over there actually. Okay. So it says, if we set v equal to j, when we're thinking of, well, let's in fact, let's just copy this, paste it in. Oh, serpent. Weird. Okay. So with this in mind, if we set v to j, we find the correct answer. The ith component of the jth basis vector is dy, is the Kronecker delta. So let's try this. If v is equal to j, then I plus well, let's put 1 here. Well, no, I can't do that. Let me ask a question here because I'm not sure about this this syntax here. I notice that the following equation uses the I in the ket notation. Is it simply saying that all of the components of the vector are set to the iteration number? V is equal to sum I v sub I. No, not that one. I don't mean to do that. Some v is equal to the sum from I ket I v. So here I need to be careful. So I noticed that the following equation uses the I in the ket location. Is it simply saying that all of the components of the vector are set to the iteration number? Would be, so v equals the sum of I 0, 0. Oh, okay. Let's just imagine this. And the second where 0 would become 1 and then 2 as the iteration continues. Let's see what that says. It's going to say no, right? Because that's exactly not what it means. The equation v equals sum of I is an expression of a vector, v, in terms of its basis representation. Here the I are the basis vectors of the space, and the sum runs over all the basis vectors. The expression IV is a projection of the vector v onto the basis vector I. It gives the component of v in the direction of I. Multiplying this by the basis vector and summing over all I reconstructs the vector v in terms of its basis representation. Notation doesn't imply that the components of the basis vectors are set to the iteration number. Rather, I is just an index labeling the different basis vectors, and the basis vectors themselves are fixed vectors in the space that don't change as you sum over them. For example, in a two-dimensional space with the standard basis, the expression would look like where 0 and 1 are the standard basis vectors and the coefficients 0v and 1v are the components of v in that basis. Oh man, today is not the day to learn this stuff. Oh my god. Can you simplify that? Can you expand on this? It went over my head. So yeah, I should check my blood sugars because that really did go over my head. Ah, it's fine. 7.2 actually probably requires me to have an insulin unit. One sec. Okay, because it's starting to go up. It'll kick in an hour. Okay, cool. Right. So certainly, let's break down the equation and explore it with more detail. Consider a vector space V. For simplicity, let's say it's a two-dimensional space over the complex numbers. We have some vector V in this space that we want to represent in terms of a basis. Choose a basis. A basis is a set of linear independent vectors that span the space. In our two-dimensional example, let's use the standard basis vectors. 0 equals 1, 0, and 1 equals 0, 1. Define the vector. Let's say vector is a specific vector in this space, such as v equals 3, 4. Compute the projections. We want to find how much of v is in the direction of each basis vector. We do this by taking the inner product of v with each basis vector. 0v equals 1, 0. 0v equals 1 times 3. Yeah, okay, got you. Reconstruct the vector. Now we can represent vector as a linear combination of the basis vectors, weighted by these projections. The vector is now 3 times that plus 4. In the sum notation, this is equal to 0, 1. So the equation is showing how to express a vector in terms of a chosen basis by computing the projections or components along the basis. Yeah, okay. So I was right. Okay, cool. Good. But because the basis vector by by basis vector, this is a separate vector, not something to do with v itself. E.g., this you can't. I wish you could just copy that. Would be is saying that v is a vector and I is an entirely new basis vector, and it just so happens that those entirely new basis vectors would be equal to 2v after the function is run. Yes, you got it. Okay, so let us make sure the basis vectors look as they should. If we set v to j in equation, we find the correct answer. The ith component of the jth basis vector is Kronecker y. So this let me rewrite this, it's confusing me. So I've got 1, oops, like that, plus, well, okay, it's actually just that, isn't it? Plus 1, or is, yeah, let's do that. Plus 2. And it's saying that that forms the Kronecker delta, which the Kronecker delta um, is this inner product of wow, okay. I've lost it because if we're multiplying with the basis vector, then it'll be, does it actually tell us here? It's saying vector equals the sum of vi to I. Thus, for example, the column representing basis vector number 4 will have a 1 in the fourth row and 0 everywhere else. Thus, for example, the column representing basis vector number 4 will have a 1 in the fourth row and 0 everywhere else. The abstract relation becomes, in this basis, is equal to 1, 0, 0, 1. Oh, I see. Oh, I see. Okay. Wow. It's not inferable from this basis vector. Unless the basis vector is something very special. And I guess it is kind of alluding to it here, right? How much have we got? I tell you what, I think I have to call it for a second because nothing's working in my brain. I think I just need some food. So um I shall come back. I shall come back. Oh well, actually, I won't promise because I might be too tired after, but the plan is to come back. We'll see how this goes. I'm really sorry to cut off halfway through this, but um this was not obvious to me, and that's because I'd missed the fact that this basis vector means this, right? And I think this had confused me certainly, you know, so, or yes, you've got it. So maybe it says it, I didn't even read it. The basis vectors I are a set of linearly independent vectors that form the basis for the space where V resides. They are not part of V itself, but provide a framework for representing V. The equation V is equal to the sum of I, yeah, is saying that you can express the vector V as a linear combination of the basis vectors I, with coefficients determined by the inner products. In other words, this equation allows you to decompose, yeah, this is a fundamental concept in linear algebra and quantum mechanics, as it allows you to work with vectors in various coordinate systems by choosing different bases. It provides flexibility. I mean, let's leave or depart this with that question, which is, so to be clear, a basis vector like so is a specific component that is set to the number passed into that vector. So let's just do it. If there were more, the dimension would get bigger, but the pattern and premise would remain. If this is right, can you show um, why this is a basis vector? It's a basis vector. It's a basis vector because if you were to uh, yeah, no, I actually don't know. You're on the right track. The vectors 0, 1, and 2 that you've written down are examples of the standard basis vectors in three-dimensional space. These vectors are. To show why these are basis vectors, we can show that they are linearly independent and that they span the space. A0 plus B1 plus C2 is equal to. They are linearly independent because no combination of these vectors, where the coefficients are not all 0, will add up to the 0 vector. That is, there are no scalars a, b, c not all 0 such that. Oh yeah, okay, cool, right, yeah, we get it now. Good. They span the space because any vector v is this three-dimensional space can be represented as a linear combination of these vectors. They span the space because any vector in this three-dimensional space can be represented as a linear combination of these vectors, where v are the components of v. The standard basis has the convenient property that it is orthonormal, meaning that the basis vectors are both orthogonal to each other and have unit length. This makes the calculations involving projections, decompositions, and coordinate transformations particularly simple. But remember that while the standard basis is often used, it is not the only possible basis for a vector space. Any set of linearly independent vectors that span the space can be a basis. That's a good place to end. I absorbed something there. I might be back soon. So have a good weekend.